Hello, everyone. I'm Leslie Lane, the chair of the astronomy department here at Illinois. It's a great pleasure to welcome everyone in person and remotely to the 2021 Iben Lecture on Astronomy. The Iben Lecture series was started about 24 years ago, thanks to the generosity of our own Icko Iben Jr., a distinguished professor emeritus of astronomy. Professor Iben made a lasting mark on astrophysics and on this campus. He's an architect on the theory of stars and is famous for revealing the turbulent death throes of stars like our sun. Professor Iben pioneered the use of computers to do science, setting the agenda for our department and really the whole campus. The Iben Lecture celebrates scientists who embody a research spirit of excellence. In addition, this is our Department of Astronomy's 100th anniversary. So we are doubly excited and delighted to introduce to you a renowned astronomer and an Illinois PhD alum, Professor Vicky Kalogera. Vicky is the co-founder and current director of the Center for Interdisciplinary Exploration and Research in Astrophysics, Sierra, and the Daniel I. Linzer Distinguished University Professor in the Department of Physics and Astronomy in the Weinberg College of Arts and Sciences at Northwestern University. Vicky is a leading astrophysicist in the LIGO scientific collaboration, LIGO being a telescope which first detected gravitational waves in 2015. Vicky is an expert in the astrophysics of black holes and neutron stars and in gravitational wave data analysis. She also studies the formation and evolution of stars and the remnants detected as gamma ray, X-ray, and radio pulsar sources in the electromagnetic spectrum over a wide range of stellar environments. Her research involves methods from applied mathematics, statistics, and computer science with using extensive high-performance computing. For her research, she's been recognized by numerous awards, including being named a 2021 Guggenheim Fellow, being elected to the U.S. National Academy of Sciences in 2018, and an American Academy of Arts and Sciences in 2021. She has served the professional community in several roles, including as co-chair of the Committee on Astronomy and Astrophysics of the National Academy of Sciences. We're in for a great talk, and there'll be time for some questions afterwards. And if you're on Zoom, you can chat your questions to us, and we have someone here read them off for us. So without further ado, please join me in welcoming our distinguished Iben Lecturer of 2021, Professor Vicky Kalogera.
Thank you, Leslie. Can you all hear me? Great. Thank you for being here tonight in person, and thank you to everybody who connects remotely. It's a great pleasure for me to be here tonight to give this special lecture, to be here to celebrate 100 years of the astronomy department, where I spent 5 years of my life trying to become an astronomer. Of course, Professor Iben was around at that time, and I took his courses, and I learned stellar structure and astrophysics from him. But I'm also delighted that my own PhD advisor, Professor Ron Webbing, is in the audience in person right now. And of course, I've come to campus before. It's not my first time after almost 30 years or 25 years. But tonight it's a very special pleasure. So thank you for being here. So what I'll tell you tonight is a discovery that involved the effort of many people, hundreds and close to 1,000 people over many years. By now, we're approaching 50 years of effort. And when the discovery happened in 2015, and since then, I must say it has changed the life of all the people involved in this effort. And I might say it has kind of changed a little bit astrophysics. I'd like to tell you about what this is, how we got to be involved in this effort, how we got to reach the point of discovery, and what has happened since 2015. Okay, so can you see my pointer on the screen? Yes, perfect. Okay, so on this first slide, already I'm showing you the very first discovery. The very first discovery happened, the signal arrived on our detectors, on our gravitational wave telescopes. We'll talk about all of this in a minute, okay, all these buzzwords. On September 14, 2015. And the signal we received is this scribble, okay? believe it or not, to us, this was extremely significant. And this was recognizable as something we have been waiting for decades to happen. And it was almost unbelievable that day. In fact, many of us absolutely did not believe that this signal was real. We were certain that this signal was a test for our analysis, for our detectors, and that soon, a few weeks later, we would be told by a very small number of people in our collaboration that this was all a test, and yes, our instruments and our data analysis is all working great, and let's move on and wait for the real signal. Turns out this was a real signal. It took us many months to convince ourselves. And it took actually, for many of us, it took receiving more signals to be really convinced that this is a cosmic phenomenon. In addition to that, what I'm showing you here on this slide is I'll try to avoid this booming noise with my mic from time to time. What I'm showing you here is a photo of this, the skyline of Chicago. And then on top, there is this gloomy gray curve, which is actually a piece of the surface of a hypothetical neutron star. We're going to talk about what a neutron star is. And it is to scale to show you how big a neutron star is compared to a big city like Chicago. And this image was produced at Northwestern for the press conference that announced another significant discovery that happened a couple of years later in 2017 that involved neutron stars. The first discovery involved only black holes. Again, I'll explain all these terms in a few minutes. Be patient. The reason I like to start my public lectures with these two images is because, of course, the first one still, gives me goosebumps, to be honest. And I think it is a little ridiculous looking because probably to you all, it looks like nothing. It looks like maybe a small child's scribble on a piece of paper, not even a drawing. And then the second image of Chicago with this gray glooming curve on top of it, I like showing because it made the cover of the science section of the New York Times, and I loved it because I was joking with the science writer that he had to post a Chicago image in the New York Times, and I really loved it that day. Okay, let's get started. So first, I mentioned black holes and neutron stars. And let me just tell you that these are very compact objects. Neutron stars are some of the most they are the most compact objects, three-dimensional, that we have in nature and we know of in nature. And black holes represent the ultimate compact object we understand exists in nature. But it's not really three-dimensional, although for the purposes of this talk, we'll be thinking about it as being a three-dimensional and having some kind of a radius and a size. But it actually represents the ultimate win of gravity that brings matter into an ultimate collapse. And really, to the extent of our current theories, that collapse leads to all matter coming and collapsing into a mathematical point. So it's not a three-dimensional object. However, we think of it as a sphere because there is a spherical surface around that point I mentioned, where if you're inside that surface, then you cannot escape the gravitational field of the black hole. Even if you have the speed of light to travel with, you cannot get out of the black hole. Okay? So for us, the black hole has, for our purposes tonight, the black hole has a surface, and that's this imaginary three-dimensional sphere around the point, which basically hides everything inside the inner parts of the black hole. Now, black holes and neutron stars are really corpses. They're stellar corpses, okay? They form when stars die. Now, not stars like our sun, but stars that are more than 10 times the mass of our sun. So a regular star, like our sun, will be an average star. Our sun is an average star. And it will eventually become what we call a red giant. I won't spend much time here because it won't form a black hole or a neutron star. Eventually, it will shed a lot of mass in a spectacular, beautiful planetary nebula. And it will form another type of compact object, but not as compact as a neutron star that we call white dwarf. What we're interested in tonight is neutron stars and black holes. And those, as I said, form when really massive stars, 10, 20, 30, 50, 60 times the mass of our sun, go through their life. They shine. They're very bright stars. They consume their nuclear fuel in their centers. And at some point, they run out of fuel. They run out of energy. And they cannot produce more energy in their center. And then the gravity of their own mass brings them into a collapse. And at the end, what remains is a tiny little compact object, a black hole or a neutron star. Now, before the discovery I'm going to tell you about in gravitational waves, did we know black holes exist? And I'll tell you, yes, we had very, very strong evidence that black holes existed. So strong that actually most astrophysicists did not doubt that black holes existed. Okay? It wasn't direct evidence. It was indirect evidence in many ways, but there was no real doubt in the scientific community. How did we know black holes existed? Well, because most stars actually don't live their lives in isolation, not like our sun. Our sun is kind of unusual in being solo in its life. But most stars live their lives in pairs, in binaries. They have a companion. And if one star, very massive, forms a black hole, then it is possible to keep its companion, despite its violent collapse and the formation of the black hole, and have a companion next to it. But once the black hole is formed, it turns out the black hole becomes a mean, vicious companion. And what happens is that its gravity now, it's so strong that it starts feeding off its own companion. So the star next to it, a regular star, maybe something like our sun, will expand, and it will start losing gas from its surface, and the black hole will accrete it. Through that mass accretion process, we get emission of X-rays, electromagnetic waves. And with the study of X-ray binaries, as we call these systems, since the early 70s, over a collection of lots of observations, we were able to conclude that actually whatever lies in the center of this accretion flow is a black hole. I will not take the time tonight to explain to you how we concluded it's a black hole, but I'd like to point out that we were not surprised, or we were not completely, in theoretical space thinking that black holes exist. There was evidence from electromagnetic astronomy. Same with neutron stars. We knew that neutron stars existed through electromagnetic astronomy. So neutron stars, as I said, are also stellar remnants. And their typical properties is that they are about 1.5 times the mass of the sun. But they're not as big as the sun. They're just about 20 miles across. So imagine how compact this is. 20 miles across is like as big as Chicago and its suburbs. Okay? And you fit in there the mass of 1.5 times the sun. So how did we know that neutron stars existed? Well, it turns out that in the late 60s, so again, right around the early 70s, just like with black holes, neutron stars were discovered in radio waves. Black holes, X-rays, the story started. For neutron stars, the story started from radio waves. And Jocelyn Bell Burnell was a graduate student in Cambridge, and she actually was looking for something completely different in her data, in her radio data. And what she found was a periodic signal, which eventually, with discussions with her advisor and other collaborators, people concluded that the source of this periodic signal in radio waves is actually coming from a neutron star. Now, what causes the periodic wave? I won't spend much time because it's not the topic for tonight, but basically the periodic signal is coming because the neutron star can act like a radio lighthouse, and the beaming of the lighthouse is misaligned from the rotation axis, exactly like you see in the movie here. And every time the radio beam hits our line of sight, just like with a lighthouse, we get a little radio signal. And that is periodic, consistent with the rotation of the neutron star. So both black holes and neutron stars we knew existed in the universe, okay? Through a lot more observation and information that I'm describing here tonight, but the communities for decades were convinced. So we keep that aside. Black holes and neutron stars. Stellar remnants, we were aware of them. There was experimental evidence. Now let's talk about astronomy as a field. Modern astronomy, we feel that modern astronomy started when Galileo started using a telescope and pointed it to the sky. Of course, astronomy really started a lot earlier when ancient Greeks and Egyptians and Chinese and probably other people looked at the sky. So the first telescope was our own eye, okay? But modern astronomy started with a telescope where you put an actual glass lens and you started making observations of things that our own eye cannot see. For almost 300 years, astronomy was based on optical observations, observations of things that emit light that our eye can detect, okay? So visible light, optical light, whatever you want to call it. It turns out, though, that in the 20th century, we had a whole revolution happening in the field of astronomy. Over about a century, and especially around the 60s, a lot of things happened. The 60s were interesting in many different ways. A lot of other fields of astronomy opened up. But all of them were using the same type of wave, an electromagnetic wave. An electromagnetic wave is basically, a wave is always some kind of an oscillation, and an electromagnetic wave is oscillations of electric and magnetic fields, and they propagate with the speed of light. And all electromagnetic waves have the same kind of nature based in the way I'm describing to you. But you need different detectors to detect them. So over the years, we went from just having visible astronomy, and down here there's a timeline that is hidden by my slide here. So we started back in 1600 with visible astronomy. And then in the 30s, radio astronomy started. And then in the 60s, we had gamma ray, X-ray, and microwave astronomy, the same microwaves that are in the microwave ovens we all use. And then eventually, we opened up infrared astronomy. What does this mean when I say opened up? Basically, it means that we developed the right technology to create telescopes or detectors that can receive that kind of light, X-rays, gamma rays, infrared light, from cosmic sources, and then we can discover things we had not seen before, because those things, for example, did not emit visible light, and we could not see them before, okay? So a century of technology advancement basically led to opening up to what we call multi-wavelength electromagnetic astronomy, because all these different types of segments of the electromagnetic spectrum correspond to different wavelengths of the wave. And every opening needed a new technology, different types of telescopes. Some look like normal telescopes, tubes with something at the end, a mirror or a lens. Others look like dishes, and others have to be in space. But at the end, we covered everything from radio waves up to X-rays and gamma rays. And a lot of technology applications came out of this research that now we use in our everyday life. Now, in 2015, what we observed was not another segment of the electromagnetic spectrum. What we observed and detected was another type of wave. Okay? So it was something called a gravitational wave, and we received these types of waves through the collision of two black holes. So I showed you earlier how a black hole can find itself in orbit or in a pair with a regular star. It turns out two black holes that came from the death of two massive stars can find themselves in an orbit, and through the emission of gravitational waves, that orbit can shrink, and eventually the black holes collide, and that last fraction of second, our new detectors, we finally got the technology of gravitational wave detectors, were able to detect. And the first detection happened on that day. So let's start from, so I'll tell you that story and what it means, but let's start from the question of what are gravitational waves, okay? So first of all, waves. It must be some kind of an oscillation. It will have a frequency, it will have a period, something is going up and down, okay? Now, what is it? For electromagnetic waves, it is electric and magnetic fields are oscillating, and electromagnetic waves are connected to charged particles, electrons, for example, that are moving and are getting accelerated. Gravitational waves are of different nature. They're not connected to charged particles. They're actually connected to mass, any mass. And if a piece of mass is being accelerated, then it can produce, provided some other conditions, it can produce gravitational waves. The gravitational waves are oscillations of the space geometry around the mass. Okay? I start sounding weird now. I'll have some movies in a minute to make that a little more understandable. As I move my arms right now, I'm creating gravitational waves. Okay? The frequency is rather slow because I'm not that fast of a mover. And the intensity of the gravitational waves I'm producing is extremely small because the mass of my fists and my arms is very, very small. But when two black holes of, let's say, 20 or 30 times the mass of the sun are moving one around the other at a fraction of, not a small fraction, but let's say a third of the speed of light, then they're producing the strongest possible gravitational waves. And then, if we have the right technology, we can detect them. All right, so let's stick to what are gravitational waves. And now I'm going to use 3 slides, 3 or 4, I don't remember, to guide you from Newtonian gravity, the apple falling from the tree, to Einstein's gravity, the theory of general relativity. Okay. So Newton's gravity had basically the following understanding. If I have two masses in space, in this case, a blue ball and a yellow ball, then the two masses are attracted to one another. And this attraction is instantaneous and automatic. And that's the gravity force. And there is no real explanation in Newton's theory, but it exists. We can measure it. We can measure what it depends on. And it keeps objects in contact as if there is a rod connecting them. And if I give a kick to one of them, then one can go around the other. So in Newton's gravity, one object can move around the other object. And the masses can move but space and time around these masses is unaffected. Okay, so you see now the grid around the masses is the same way we experience space around us. So if I put two masses here, the table remains flat. Or more importantly, because the table will remain flat anyhow, the geometry of an imaginary grid, if I had around two masses, remains flat. Einstein looked at this in a different way and basically concluded, or the concept was, that actually mass interacts with the geometry of space and time, but I'm going to leave time aside. We don't need it tonight, okay? So mass deforms and warps the geometry of space. And what this means is that even if I place, this is my flat geometry when it's complete vacuum, but if I place a mass in that vacuum, then the geometry of space gets a dimple around it. The same, the way you see it in this graphic. Oops. The same you saw it in this graphic. Okay? You saw the dimple under the masses. And of course, if you have that dimple, then you see the grid of that space, the geometric distances of reference points is changing. It's no longer the same distances like a nice square grid. Now, if now you have two masses and the space around them is no longer flat, but instead it's curved, think of a membrane that is flat and tense, and you stretched it, and then you put two balls in it, and the membrane sinks. If you now take a marble and you let it on that membrane, it's gonna move, and it's gonna follow the geometry of the space. It's gonna follow the geometry of the membrane. It's gonna follow the curvature of that membrane. The same happens with masses in curved space. Space-time, but we're leaving time aside. So, and then through that motion, and really through the acceleration of masses, oscillations, not only you get the curvature of space, but the space can start oscillating. So let's look at this. This is the visual to have in mind. You see how the waves now get formed right around the two masses, one going around the other. And then you can see these ripples now propagating further away from the source. What is the source? The source is not a set of charged particles, but the source is two masses moving. Okay? So these are gravitational waves. What is the oscillation? Well, you can see it in the visual here. If you pick any given space point here, you'll see that it kind of goes up and down, up and down, up and down. So it stretches and gets squeezed and stretches. So that oscillation is the wave, the gravitational wave. But the waves travel with the speed of light. It can be proven through the math of general relativity. And they can travel through the universe. And if you have the right detector, if you have the right technology, then you might detect it. Okay? Now, waves carry energy, like any wave carries energy. And it turns out if two things are moving one around the other, you're disturbing the space, you're creating ripples, like you threw a stone on the surface of a lake. And waves now are being generated, and they need to travel. They're going to travel, and they're going to move away from the source, like light moves away from a bulb, let's say. They're going to carry energy. Where is that energy coming from? It's actually coming from the motion of these masses. So that circular motion, one around the other, is being affected by the emission of the waves. And as the pair is losing energy, the orbit shrinks and decays. And the black holes are coming closer and closer to one another. And eventually, they're going to touch. Now, black holes are not three-dimensional, but what's going to touch is that imaginary spherical surface I talked about. and they're going to merge. Okay? As they come together, they move faster and faster because remember the spinning ice skater, if they close their arms, they go faster and faster. Same thing, the black holes are coming together, they're going faster and faster. And because the black holes are coming together, the gravity actually becomes stronger, and the oscillations close to them become more violent. So we're going to see this behavior in the signal we detected. Okay. Now, I asked the question, did we know black holes existed? Yes, not through gravitational waves. Did we know neutron stars existed? Yes, not through gravitational waves. Did we know gravitational waves existed? The answer actually is yes, but not through the direct detection of gravitational waves. How did we know? Well, it turns out it goes back to neutron stars behaving like radio lighthouses. So soon after the first discovery of the first neutron star, another neutron star, another pulsar, radio pulsating source, was discovered in '74. And soon after, the discoverers, Joe Taylor and Russell Hulse, advisor and student, but Russell Hulse moved away from astronomy eventually. They realized that this neutron star pulsating radio source they discovered is actually in an orbit with another neutron star. Okay, how they realized that? Not for tonight. And they were able to understand the structure of the orbit of the two neutron stars. And through radio wave measurements, over many years, over about a decade, although it took less to get a hint of this, they figured out that the two neutron stars are coming closer and closer to one another. And it turns out how fast that orbit was decaying was perfectly consistent within measurement errors, consistent with the prediction by Einstein based on general relativity, connected to the emission of gravitational waves. So through radio waves, we had an observation that implied that you have two compact objects moving in an orbit that is decaying, and the rate, how fast that decay is happening, is consistent with how much energy can be extracted and from the motion due to gravitational waves. So over the years, people got convinced that, yes, gravitational waves is the only explanation for this orbital decay after doing many, many tests. And the pair here won the Nobel Prize in 1993. I was actually a graduate student here in Urbana, and I remember the day it was announced. Okay, so the next question is, all right, we know black holes exist, we know neutron stars exist. We cannot actually directly detect them. Now we know there's a new type of wave out there that we cannot detect directly, but we know it affects cosmic sources. And then it became, people realized that actually there could be things that can only emit gravitational waves. For example, black holes. Neutron stars can appear as radio pulsars, but two black holes, they cannot emit light because they absorb all of light. The only thing they might emit is gravitational waves. So this and other reasoning was a great motivation for people to decide how can we build a telescope to detect gravitational waves. Now, mind you, when Einstein developed the theory and realized that the theory of general relativity that describes gravity has an implication that gravitational waves might exist. Certainly the math gave that implication, whether it's nature or not. Not everything in math is actually reality. Eventually, people got convinced in the 50s that this might be reality. He calculated how strong gravitational waves might be for cosmic sources, out galactic distances. And he realized that the distortion in space is minuscule. And his conclusion was, okay, this is inconsequential and it will never be discovered. Okay? So that's the background. Okay? So under that background, a group of people, mid-60s, late 60s, early 70s, started working nonstop and obsessively, really, trying to figure out how to build a gravitational wave telescope. Now, if you want to detect something and you have some theoretical description of what is it you're trying to detect, some phenomenon, some radiation, some motion or whatever, what you really want to think about is what is the effect of this thing on material or on things you can control, okay? That's how you start. So what is the effect of gravitational waves on space and time, but we stick to space? It's actually this motion that you see here. So if I have a circle that is undisturbed of points, and there's no gravitational wave around, and let's say that circle of points undisturbed is on the plane of the screen, and then a gravitational wave travels perpendicular to the screen with the speed of light, then it's going to cause the space, the geometry of space, to change in this periodic way that you see here, okay? It's a very particular way of oscillating, okay? There is these two polarizations, we say, okay, the cross and the plus. It has a certain frequency, and there's other characteristics associated with it. So people focused on how can we detect this kind of oscillation in space, but they were faced by the fact that I told you. These waves are extremely weak. So it's like our bulbs are so weak that, our eyes, like the stars that our eyes cannot see. And you don't know how to build an optical telescope. So you're stuck. People started thinking, how can we do this and cross that boundary? The problem is that for a typical gravitational wave source, at a typical distance, if you take the whole Earth and you say, how much stretching and squeezing the whole Earth will experience if a cosmic gravitational wave goes through it? The stretching and squeezing is as much as the size of a proton. Okay, I'm not putting any numbers here, but think proton. It's not even an atom, it's a proton inside the nucleus. The whole Earth. This is the kind of measurement people tried to make. And when some people, I'm going to show you one of them at least in a minute, told people that they think they have a way, at least in design, everybody else looked at them and said, well, you're crazy, okay, because that's just not possible. Okay, so now there were many ideas for how to detect gravitational waves, and I'm not mentioning them today, but the type of gravitational wave telescope, quads, that actually manage to detect directly a source, uses what we call laser interferometry. And it doesn't look like a telescope at all. I'll show you the real facilities in a minute. But it is based in this configuration. You have a source of laser somewhere. You're going to see it in a movie in a minute. It sends out a laser. It goes through an optical element that splits the laser in two. One part travels down this way, another part travels down that way. Here, you hang mirrors and you make them be as perfectly isolated from any disturbance as you can. They bounce off these mirrors, they come back, they connect the two lasers, and then you study their interference, and you try to see, did my mirrors move by that kind of minuscule quantity, stretching and squeezing, stretching and squeezing, stretching and squeezing, and did it happen with the characteristics of that cruciform manner that I showed you earlier? So here's the principle. I just described you this. The motion here is horribly exaggerated. We wish it was that big, although we don't wish it was that big, because if it were, then we wouldn't feel very good with every gravitational wave going through us. And then, you know, with analysis of the data you collect here in the combined laser beam, you can figure whether your mirrors were affected by something from cosmic sources that behaves like a gravitational wave. It's a lot more complicated, okay? But, and of course, there is a lot of things to worry about because there's many other things that can make those mirrors move, okay? But this is the principle. And the principle was proposed by this dear guy here, Ray Wise, who eventually, when I joined this collaboration, turned out to become my mentor. Predictions for how strong the waves are going to be were led at that time by another colleague of Ray's, Kip Thorne, Ray at MIT, Kip Thorne at Caltech. And Barry Barish eventually led us and building the right detector and led us to the discovery. And the three of them received the Nobel Prize when the discovery was finally made. I told you that hundreds and thousands of people were finally involved in this. It's not these three people, but of course, you know, the seed of how to develop the technology is an extremely important step. The project, I think the idea was conceived in mid-70s. Funding was finally authorized in early 90s. I joined, of course, not an important step in the history of the project, but important for me. I joined in 1999, I think, and we didn't get a discovery until 2015. And yet we kept working, and people kept funding us. That's a miracle in itself, but I won't go further there. Okay, this is how the detectors look like. We have two detectors in the US, one in Louisiana State and one in Washington State. And basically, what do you see here? You see the corner station where the laser starts, and you see the two arms at 90 degrees, corner station and two arms at 90 degrees. They are about 4 kilometers long. So two and a half miles or so, okay? And at the end of these tubes, there are suspended mirrors, and then the lasers come back, and then we analyze the signal at the corner back. All right. And then Italy, do I have the name? Italy and France collaborated, and they built a European detector as well, a little bit in parallel, a little bit after the US, but we were all collaborating. And that's how then you make a scientific community of 1,000 people who are all working together for about 20 plus years to try and get to this discovery. Now, I want to go back to how incredibly crazy it is that this measurement is possible. So how small is actually the stretch and squeezing that LIGO had to achieve, the kind of measurement it had to achieve? I should tell you that it is the most precise measurement in any field of science and engineering ever made. I should also tell you that I am involved in the data analysis, and I have nothing to do with making the detector, thinking about the detector, or reaching this kind of achievement of this precise measurement. But without the telescope, we could never do the astrophysics we are doing today. Okay? So the stretching and squeezing is 10 to the minus 18 meters. Now, does this say anything to you? To be honest, it doesn't say anything to me if I just think about it as a number. So let's break it down. What is 10 to the minus 18 meters? Well, if we take 1 meter, so it's about 3 feet, okay, and then we divide it by 10,000, then we're going to get the thickness of a human hair, okay? Not the length, the thickness. If we divide that thickness of a human hair by another factor of 100, then we're going to get down to the wavelength of visible light. If we divide that by another factor of 10,000 again, then we're going to go down to how big is an atom, typically. If we divide yet by another factor of 100,000, we're going to go down to how big is a nucleus, typically. And then if we divide by another factor of 1,000, we're going to go to how small the stretching of the mirrors in LIGO, LIGO being the gravitational wave telescope I talked about, is and is being measured. Okay? So it is unthinkable, and yet it has been achieved. Now, before I show you, before I go to the black holes, really? Okay, then I'll skip this. I was going to tell you, I'm being told I have 5 minutes. I'll tell you, maybe we'll get to that in the questions. Gravitational wave telescopes are not telescopes by any means, but they actually operate a lot more like our ears. You know, telescopes behave like our eyes, but gravitational wave detectors behave like our ears. They're sound detectors. But please, please, please don't leave this lecture thinking Vicky Kalogera told you that gravitational waves are sound waves. Okay? They behave like sound detectors. They're not sound detectors, and gravitational waves are not sound waves. We can come back to that. No, we don't want this video to start. So, on August 14, 2015, we turned on the advanced stage of our detectors, and this signal appeared in our data. And it is miraculous that if you looked at cleaned raw data, you could actually see the oscillation. So I want to show you a couple of things. First of all, no, it's not scribbles. Yes, it is statistically significant. And what you see here is the strain, which is basically the fractional change of that oscillation in space. It goes up and down, like a wave. And as a function of time. And what do you see? Well, the amplitude of the wave increases as time passes. Why? Because the black holes are coming closer and closer together, as I told you, as the ice skater pulls their arm further in, and they're moving faster and faster. Acceleration is higher and higher. The gravity is stronger and stronger. The gravitational wave is stronger and stronger. So the oscillation amplitude increases. In addition to that, if you look at the distance of the peaks, becomes shorter and shorter in time. That means the frequency of the wave is increasing. The period of the wave is decreasing, okay? And that's because the motion becomes faster and faster and faster. So we were able to take this data. When we compared them to the when we compared the data to the prediction of Einstein's theory, we got the thin lines you see here on the plot. And you can see the spectacular agreement. And confirming again Einstein's theory of general relativity, not the first time. And of course, we have two detectors, as I told you, Louisiana and Hanford. And it was really important to have two detectors, because if it's a cosmic signal, it better affect both detectors. If it's a noise locally, it may happen only in Louisiana, but not in Washington. Okay, I'm thinking of the map looking above from the USA map. Okay. So here's now thinking that gravitational wave detectors act like ears. Gravitational wave signals can be converted into sounds. So we're going to hear sounds, but we're also going to see the signal in another representation, which is frequency of the signal in each detector as a function of time. And I told you the frequency clearly increases as time progresses. So let's play it. Okay, so look at this image. Frequency as a function of time, it goes up like a banana. Okay, that's the in spiral, we call it. The two black holes are coming very closely together. Soon we're going to see a movie. But because the frequency is increasing, when you translate that into a sound, what you hear is a chirp. You hear a whoop, whoop. Okay? So we make that translation because actually the scientists have trained our ears a little bit, and we hear these sounds, and we can almost guess, not quantitatively, but qualitatively, how massive the black holes were from the duration of the sound and from how the frequency is changing as a function of time. Now, if you hear a lot of noise, and if you clean the noise, here's what the clean signal sounds like. In repetition, okay? So whoop, whoop. I have it in loop. We're gonna switch. I want to show you here that we also roughly located where it's coming from the sky. And that's a very hard job to do, to say where is it coming from the sky. It was coming from the south, and it hit Louisiana first, and 7 milliseconds later it hit Washington. And 7 milliseconds is how long it takes light to travel from one state to the next, that state to Washington. And gravitational waves travel with the speed of light. So that was an important test as well. Okay. Now, this is a simulation that can be produced with Einstein's theory of general relativity given the data, and it fits the data. So you see now what I've been describing to you. Two black holes, they're coming together. We're slowing down the movie. The signal is down here. We're going up and down the wave. The two black holes are touching here. And they're merging. And as they are merging, the space-time is going crazy. The oscillation is very strong. Eventually, you get a single black hole that's not moving. It's not going around like crazy anymore. Settles in, no more gravitational waves. It's not a continuous source. That's why it stops. Whoop! End. That pair of black holes will never merge again. Okay? We cannot go back and look at that source again. So that's the gravitational wave chirp. Okay, a little bit about energies. Leslie, what time? Maybe I want to give you some sense of what is this cosmic source? We can extract all of this from the data. It's a billion years, it's a billion light years away, and this collision happened a billion years ago. It didn't happen on September 14, 2015, it traveled for about 1 billion years until it hit our detectors. When the two black holes collided, the energy, remember the waves carry energy? The energy produced in that collision in gravitational waves, not in light, not in X-rays or gamma rays, but in gravitational waves, if you convert it in light as energy, quantity of energy, that collision was 50 times brighter than all the stars in the universe, not the visible stars, all the stars in the universe, the billions and billions and billions and billions. That's 3 million times the energy you might need if you wanted to destroy the sun. And the final black hole was just about 200 miles across, okay, the width of Illinois. And the two black holes were moving at the end at 1/3 of 1 billion miles per hour. My arms don't move that fast. All right. One more discovery. 2 years later, we got hit by this signal. Okay, clearly different than the whoom, whoom. So this is longer, and it's smoother. I cannot reproduce it, it's too long. And then at the end, a very high pitch. Much higher frequencies it reaches at the end. That's a collision of two neutron stars. And it turns out neutron stars are for lower mass, and they have smaller radii, three-dimensional objects, and they don't collide early on. They keep going and going and going and rotating, and they can reach a motion of a much higher frequency. And the signal lasts longer in our data, okay? Now, what was impressed, this is the comparison with the binary black hole to tell the difference, okay? Very different sounds. Okay, the banana shape, also very different. Very thin, but very clear in our data. Now, what was important with this source is that it didn't come only in gravitational waves. Neutron stars are actual matter. They're not black holes. When the two neutron stars collided, the neutrons broke into charged particles, and charged particles collided, got accelerated, and produced electromagnetic waves. And that was the beginning of multi-messenger astronomy, not multi-wavelength, but multi-messenger astronomy with gravitational waves and electromagnetic waves coming from the same source. Why is this important? Because actually, the more information you have from one source, the more you can understand about the physics of what happened. It turns out we learned a lot about that source. We detected then also visible light from that source. When I use here we, and it's not gravitational waves, it's the royal we. I was not involved in that work. In fact, a colleague of mine and ours, who was at some point a faculty here in Illinois, was involved in discovering the optical light. And it turns out the optical emission from that collision of double neutron stars comes from the formation of gold and platinum and other heavy metals. And that's where all the gold comes from that we have on the Earth. It comes from neutron star collisions, okay? There is no other way to form gold. So this is what happened. This is not 1 billion years ago. This is 130 million years ago. Because it was so close, we could see the electromagnetic waves. If it were as far as the binary black holes, we could not have. So you see the two neutron stars. This is a fancy movie that is not a scientific movie like the one I showed you before. And this was created by NASA. And when the two neutron stars lost a lot of energy in their orbit due to gravitational waves, right now in this motion, the only emission is gravitational waves. When they finally collided, they combined into a more massive neutron star. Gravitational waves propagated, but also you got jets and in gamma rays and X-rays, and also optical emission in the center. And basically, we had a whole multi-wavelength study of this source as well. The jets actually are associated with gamma ray flashes, and it was a big hypothesis for many, many years, was confirmed that gamma ray flashes are indeed produced by neutron star collisions. And that was a mystery that had persisted for about 40 years, 50 years now. So for these two discoveries, first black hole collision, first neutron star collision, our collaboration was, the discoveries was announced in 2 years in a row as the breakthrough of the year in all of science. And our lives changed forever. And when we remember of those two specific days, we remember what happened, where we were, what emails we received, who told whom what, and everything. And this is where we are now, and this is my last slide. In 6 years, we have now detected almost 50 black hole mergers. And these are all these blue triplets. And if I pick one here, this is one black hole coming with another black hole in orbit, colliding and forming another black hole. And what are we showing here? These numbers are how massive were the black holes, because we can measure that from the data. So for each collision, we have information about the black hole masses. We're trying to understand how these things are forming. The last thing we announced is that we also have now detected the mixed merger. Black hole and neutron star coming together, colliding, and giving us gravitational waves. We're doing a lot of astrophysics now. We have a whole new field called gravitational wave astrophysics, and it's been an amazing thrill to be part of this for me and all of us. Thank you.
Thanks, Vicky. We'll have a little time for questions. For anyone in the audience has a question, we can hand off the microphone. Yes, can you come down? Try to cast them. I want to make sure people online can hear you.
I was just curious to know, why was it that we could hear the neutron stars colliding for so long? Was it because of their speed or the amount of time they were rotating around each other, compared to a black hole where we just heard the whoop, right?
Yes. So what happens is that the neutron stars, so first of all, we can only, with any given detector, you can only see a certain range of frequencies. You can be sensitive to a certain range of frequencies. Our frequency band is from about 20 hertz, if that makes any sense to you, to about 700 hertz, let's say. The black holes are big, the black holes I showed in the beginning. So their event horizon, that surface where light doesn't escape, is actually quite big, and therefore the collision happens at a large distance, and that means that at that orbit, the frequency of the final collision is relatively small. For that, it was, I think, 60 hertz. But for the neutron stars, they're much smaller, and they keep going around and keep going around and keep going around. They went around for 160 seconds in our detectors, and the collision happens way above 1,000 hertz. So it lasts longer.
Thank you so much. So you mentioned that it was 160 seconds for the neutron star.
160 seconds.
How long was it for the black hole in our time?
The black hole was 0.2 seconds.
Oh, okay. Thank you very much.
Other questions?
So you said that in the case of LIGO, you wanted to make sure that it's not a local noise and a cosmic signal, but the signal came from 1 billion light years away. So what is considered local in this scenario?
Oh, local is, well, I'm trying to convert to light years. So local is the galaxies, so 1 billion years, that was, I'm trying to do the conversion now. So local is the galaxies that we identify as big galaxies. So for example, you know, the Magellanic Clouds, if you have heard of them, I'm sure you have heard of Andromeda. So that's our local universe. Maybe the Virgo cluster. That would be 130 million years. That's kind of, so I would say 50 to 100 million light years. When you're talking about billion light years, that's becoming to be not the local universe anymore.
Any more questions in the theater? Okay, we'll do 2 more and then move to online.
So you were talking about detecting the gravitational waves with mirrors, and I was wondering, were they actual mirrors? Like wasn't the thickness of the thing involved in how much they had to move to detect the waves?
So I couldn't hear the question. Leslie, can you help me?
Can you hear me now?
Yeah, go ahead.
So my question was about how you detected the gravitational waves with the help of the mirrors. Like, were they actual mirrors? Like, wasn't the thickness involved in how much they had to move?
Yeah. So, okay, so the mirrors are made from a special material. Now we use sapphire, actually. Our current mirrors are 40 kilograms, 40 kilos each. They're suspended from a very complicated suspension isolation system to avoid any shaking from seismic noise, etc. As much as we can. It's not perfect. No experiment is perfect. And no detector is perfect. I'm not sure what else is important. And it's also, it's a certain material because you don't want your mirror to actually change its shape. When the laser hits the mirror, the laser can hit the mirror material. And it can start changing its shape, and it can start moving by the momentum of the photons of the laser. So you want a material that can resist all of these to some extent, and whatever they cannot resist, we take that into account in our data analysis and how we correct and deal with the noise in our data.
Thank you.
One more question? Yeah.
Hello, Professor, I'd like to ask about, so you mentioned that the project started around 1970, but you only were able to get measurements starting 2015. So I imagine there must have been many problems and theories which were posed over these 45 years.
Yes.
And you mentioned lots of very exciting developments, detections with the labs in Washington, in Louisiana. So my question is that where do you think, what other problems are there to solve with these new tools and facilities and with the aid of gravitational waves? Yeah.
Okay, so is the question about what happened, is the question about what problems we faced up until and why it took so long?
My problem is like using these new facilities and techniques. What other problems are we hoping to solve maybe in the next steps? Yeah.
Yeah. All right. So when it comes, so first of all, these facilities can be used for many years, and we can keep improving the mirrors and the lasers and the optics and do all kinds of things to make our detectors more and more sensitive to detect sources from far away. But that's still astrophysics, okay? That's still trying to understand what's going on in the universe and trying to see, where we are and where we're going and where we're coming from. But in order to develop this technology, a lot of things were done for the first time, both in basic science, material science, for example. The vacuum that was created was the purest vacuum ever made in an experiment, and that's being used in other experiments now. The laser stability was also a first, and lasers need to be stable for other applications. The suspension system also was a breakthrough, and it's used in other applications. I don't know exactly what, but I know it's used in the industry. Now it has become more of an industry standard. There's one other thing. The material that we use for the mirrors it was developed for LIGO, and it will have applications in material science. And then in data analysis. So for our data analysis to dig and find this signal in the noise, we had to develop some new data analysis and data science methods, and that a lot of our scientists, after a few years within the LIGO collaboration, they go out and join the workforce as top data scientists.
Okay, we have 3 minutes left before I have to leave the room. We have questions from chat on Zoom. This is probably a coincidence, but is both gravity and E&M waves being able to produce waves that can propagate in a vacuum related to Newtonian gravity and classical E&M being formulated in similar inverse square action at distance? Does that make sense?
Yeah, I think I understood the question. I'll answer and then tell me. So electromagnetic waves, the further away is the source, the brightness, let's say, drops as 1 / distance square. And the question is this happening for gravitational waves?
I think the question is the fact that both types of waves go through a vacuum, is that related to the inverse square law?
Oh.
The fact that they both, light and gravity waves, come through vacuum. Why is that? Why is that a coincidence, or is it something fundamental?
No. So first of all, when these waves travel in the universe, they don't necessarily go through vacuum. Of course, interstellar medium is really a vacuum compared to the vacuum we can produce on the Earth. But in general, they interact, electromagnetic waves can interact with dust and other particles in the galaxy around stars, etc. So it's not really a high vacuum situation, and in fact, electromagnetic waves can get blocked, especially visible or in ultraviolet, etc. Even our atmosphere can block X-rays, for example. So electromagnetic waves are affected by their surroundings. Gravitational waves are actually, the reason it's very hard to detect them is because they don't interact with matter very strongly. And that's why the detectors have such a hard time detecting the waves, because that oscillation is so small. So they're not affected by their surroundings. The vacuum I'm talking about is not in the traveling from the source. The vacuum I talked about is in the detector, in that arm that the 2 lasers are traveling down to the mirror and back. I hope.
And a final question for tonight. If gravitational waves are so weak and the stretching, squeezing is so minuscule, why are they so important? Why are we driven to detect these waves?
Yes. So, well, I mean, I'll give you an honest answer. A lot of the discoveries, but I mean, I know why it was so important to Ray Wise. And to him as an individual, it was just a challenge. You know, it was his passion. It was what drives every single scientist. We don't necessarily always think about, oh, one day my basic science will help, will have a major application in technology. For him, it was a challenge, and he said, if these waves exist, then I want to build the experiment that will detect them. But in practice, why is it so important? Well, for astrophysics, it's really important because we are discovering things we cannot discover with electromagnetic waves. Some other person in my position might tell you, oh, it's really important because we can test Einstein's theory of general relativity. I would say that that was not worth all the effort, but my colleagues might disagree. But I think what's worth the effort is discovering things about the cosmos we never knew existed, or we could not be sure existed. The last thing I will say, though, is that a lot of the things we're doing now in basic science, we have no idea how they will affect technology down the road. And I'll finish with one thing. When Einstein developed his theory of general relativity, why was he doing it? He was obsessed with understanding gravity. He wasn't thinking about any application. And yet, the theory of general relativity, if we didn't understand it, if Einstein had not developed it, we couldn't make GPS work. We couldn't have localization on our phones, but GPS is important for many other things than us finding our Starbucks around the corner. So he could never have imagined that application, and this application was not what was driving him. So any individual scientist in basic science is driven by an internal passion to solve something nobody else has solved before.
Well, thank you very much, Vicky. It's time for us to go, so let's thank Vicky for a beautiful talk.
Thank you.